Hello everyone, my name is Giovanni Sanchez and I'm a part of Group 4. My team members are Dominic, Rebecca, and Emily, and today we're going to talk about regression test case prioritization, as well as the different prior works that have been used regarding this mechanism, the similarities and differences that each of these have, and of course our novel approach. Alright, let's start with what regression test case prioritization is. So this methodology is put into practice with regression testing, and regression testing is essentially a powerful technique that validates any changes made to a system. It involves testing several software applications to ensure that they function properly and meet given requirements even after they have undergone several tweaks and enhancements. However, the main issue with regular regression testing is that it doesn't consider prioritization itself. So if we were to consider a large system with an immense amount of data, regression testing could take multiple weeks to complete. So with regression test prioritization, we can prioritize tests that are found to be more effective. And this method aims to decrease the cost of regression tests by modifying the order in which test cases are executed in general. And by doing this, we can identify errors and get rid of unwanted behaviors in any software system. Alright, so one of the approaches that has been used regarding regression test case prioritization is known as Sweep Builder, and it's an effective method utilized to manage the order of regression test cases. This tool was made by Westermo Research and Development AB, and it was designed in hopes of reducing errors during regression testing. It essentially addresses test case completion during a given time frame, and it forces tests to finish relatively close to their expected runtime, so that it allows them to complete without having to necessarily abort them manually. And in this one, test cases aren't omitted because most of them are completed during their given runtime. Therefore, there's no need to ignore them. And lastly, it utilizes a priority distribution system in which regression tests are sorted based on which tests were more important. So what it means by important, it essentially indicates whichever test has a higher priority than the rest. Therefore, it'll just follow that pattern and that sequence based on whichever has the higher priority. Alright, and the next approach is known as fit test, and this one was made to give priority towards tests that could find out whichever number has the most mutations in it. And the reason we want to figure out which ones have the most mutations is because these have more possibilities of finding out whether there are any modifications done within several external services. And this one also provides quick and effective prioritization within its test. And this is because it doesn't require any manual involvement to prioritize these given tests. And it also has an effective approach towards selecting which tests to run. So it essentially eliminates the need for complex human decision making since it does it on its own. And it allows to determine which tests are much more important than the others. And it basically provides simple and fast regression test cases in general.
Hello, my name is Dominic Bell and I'm going to briefly discuss the two prior works I researched for this project. The first topic is a version of regression testing prioritization where you reshuffle the test cases during testing in order to prioritize the test with the highest chance to fail. The goal here is to find all the faults as fast as possible. The core concept is that most regression testing methods consider test cases to be independent, meaning that the result of one test has no effect on the result of another. The group behind CoDynaQ, however, argues that test cases should not be viewed as independent. This means that they believe there is a link between the result of separate tests. This concept is called cofailure. You can view an example of cofailure here. If test A fails, what are the chances that test B or C fail? If you keep a log of all of the tests that you run, you'll eventually notice connections. For example, here you can see that every time test B fails, test D also fails. After you collect enough data, you can eventually derive the failure of one test in terms of another. For example, when test B fails, you can see that test D will fail 85% of the time. This means that they have a high cofailure rate, and that if test B ever fails, you should immediately prioritize test D to see if it fails. The strengths of this methodology is that it builds better predictions the longer you use it due to finding or having more data. It also finds faults very quickly. In the paper researched for this topic, It only found the first fault about 10% faster, but it was able to find all of the faults around 60% faster compared to its competitors. The weaknesses of this methodology are that you are required to find the co-failure rates in order to use it, and you also need to store those co-failure rates along with all the tests that you run in order to keep it accurate. Here's a conceptual example of the reprioritization method. You initially start with just your default test case ordering. If the test passes, you do nothing special and you continue. But as soon as the test fails, you immediately find the co-failure rate of every other test, and then prioritize based on descending order of the co-failure rate. This means you want the test immediately after to have a very high chance of failing, and then test at the bottom to have a low chance of failing. This way, you can prioritize finding all of the failing tests immediately. So here we swap D and C because D has an 85% chance of failing, but C only has a 10% chance. After the swap is made, we run the next test and we find that D fails. After D fails, you would again find the co-failure rates and reorder. This reordering process doesn't take very long because you keep a chart of all the co-failure rates. So you would look up D and then find C and E. This is actually a fairly fast process. Our next topic is REPR, which is an information retrieval approach. IR normally is the process of scanning a document for queried data, which would be very similar to if you're using like an ebook and you use Control F to find a topic. This has been adapted, however, to work for code. Normally, code is hard to scan contextually for the objects around it due to the way code can be nonlinear. A big thing to note, though, is that programmers are taught to be fairly consistent in the naming of their methods, functions, test cases, documentation, and comments. We use these consistent naming conventions to find connections between source code and test cases. So if you made a change in the system and you made a change inside of a function, the system would notice the change inside of that function and then look for all test cases that use that function in some way. The strengths of this process is that it's relatively quick and highly accurate, assuming good naming conventions. Also, a really interesting fact is that it is not language specific. It was noted that at a loss of about 2% accuracy, it doesn't matter at all what coding language you use. It can scan anything. The weakness is that the accuracy is dependent on those naming conventions, so bad naming conventions will very much hurt the process. Also, a weakness is that while it's very good at finding the items at the top of a priority list, it is pretty much useless for finding things in the middle and the bottom. We will go deeper into this weakness for the priority list when we get to our novel idea section. So here's an example I created for the IR approach, where it's a banking example. Here we just have simple accounts for 3 people with their names and their balance. We have a function that alters their balance, so you can increase or decrease the balance. And then we wanted to add a new restriction where that bank account can never go below $5. So we added that here in this if-else statement. And then once the system detects the change here inside alter balance where this is created, it scans all of the test cases to find ones that may be related. So here you can see test case A uses alter balance, test case C also uses alter balance, but test case B does not and uses something instead called verify account. Because of this, you would prioritize test case A and C and then just push B down below them. That was everything for my 2 topics, but we will be expanding on both of them in the novel idea section to come.
An academic journal analyzed focuses on fault-based regression test case prioritization. They use these techniques for object-oriented programs where they place various bugs throughout an original Java program to test all of these different methods. The 4 different test cases used are optimized bug detection based prioritization, hard to detect bugs based prioritization, expected bug detection based prioritization, and Bayesian probabilistic prioritization. For optimized bug detection test case prioritization, a test case gets a higher rank if it detects a higher number of bugs that are not usually or commonly detected. Hard to detect bugs based prioritization will put their test cases into three separate groups, which are hard to detect, not hard to detect, and redundant test cases. Expected bug detection based prioritization uses an algorithm to calculate the probability of a bug being detected and then calculates a value for each test case. Bayesian probabilistic prioritization is based on a probability calculation with the same name. The test cases are prioritized based on the likelihood of a test case detecting a bug. Once these priority rank lists are produced, they are given as input to the ensemble ranking methodologies, which are averaging, Kendall-Tau, and the Schultz algorithm. The average methodology does essentially what the name says. It'll take the averages of all the different ranks created. The Kendall-Tau ranking calculates by comparing discrepancies between two different rank lists. It'll create subsets of the conflicting pairs and keep repeating that process until it produces a final result. And the Schultz algorithm is just used for ranking. It makes a list of test case preferences and the strongest path and will return a prioritized list. The conclusion that was achieved through this testing and found in this academic journal utilizing fault-based regression test case prioritization. They evaluated 16 Java projects, and in first place for the test case prioritization methods was the optimized bug detection based prioritization. Another academic journal that we analyzed focuses on the learn to rank method for regression test case prioritization. In this study, they combine the extended finite state machine features, specifically the random forest algorithm, to evaluate any proposed method's performance in terms of the average percentage fault detected. The model-based test case prioritization speeds up the process of testing where the models and test cases are ranked because the models are typically high-level descriptions and it tends to be simpler and quicker compared to other test case prioritization methods. The learn to rank method is a technique that utilizes an algorithm that will learn as it goes and creates a model that is ranked. The model-based test case prioritization methods analyzed in this study are slightly modified to fit the version that they wanted to see for testing in order to create their own contribution. These minor modifications are marked and appropriately called marked transitions, and then they outline 8 different model-based test case prioritization methods. Other contributions that they found before making this one considered using only one characteristic of the extended finite state machine, but they wanted to look into the possibility of using more than one. With the multiple methods and the existing learn to rank technique, they created a new method, which is called the learn to rank test suite. There's 2 phases to this process, which are training and deployment. In the training phase, they place faults inside the programs, inside the methods, and then using the heuristics previously mentioned, they generate different rankings for the test suite. They perform tidying and then utilize the learn to rank algorithm to produce a final ranking model. And then in the deployment phase, they add new faults and do another similar act, and finally put the data in the ranking model to create a score for each test case and prioritize the one with the highest score.
So for genetic algorithm, it is a search method that utilizes the principles of genetics and natural selection. Here on the diagram on the right, you can see that it starts off with a new generation where you want to evaluate each individual for its strengths, its weaknesses, and see what you want to select for. Go through with the selection, it will reproduce, mutate, and then you'll end up with a new generation again. And going through the cycle, you'll end up with the optimal solution for your current problem. Each variable is encoded into a finite length string of an alphabet, where each string is called a chromosome, the alphabet is called a gene, and the values of the said genes are called alleles. And in our case, the chromosomes are the test cases. It also uses a fitness function that will give each chromosome a fitness value, and this value is how we're going to prioritize each test case against each other. It typically focuses on code coverage, so whichever test case can cover more code, it'll give a higher fitness value to it. And the algorithm produces the most optimal solution available. So not the most optimal solution overall, just whatever is given at the time, it will give the most optimal solution at that time. If you keep running the algorithm over and over again, it will create a solution that is almost near optimal. For swarm intelligence, it mimics the nature of natural self-organized groups such as bee colonies, ant colonies, cat swarms, etc. They consist of agents that are assigned to a single test case, and each agent interacts at random, so there's no predefined rules on how they're supposed to behave with each other, and these interactions give rise to an intelligence. It utilizes a fitness function that assesses each agent against a formula designed to represent the most optimal solution for the current problem, and it gives each agent a fitness value. And since each agent is a test case, this is the value is how we're going to prioritize each test case against the other. Um, it also improves the efficiency of determining prioritization of each test, thus optimizing regression testing in the long run. And for the comparison part of our report, it focuses mainly on the approaches. So each solution and algorithm that we talk about for the test case prioritization all have one overall goal, which is to improve the efficiency of regression testing in the long run by improving the prioritization of each test case. And each approach that we talk about include automated tools, using algorithms to rank each test case, reshuffling the test cases and running them in co-failure pairs, and then using information retrieval methods to scan the code for changes, which then prioritize tests based on these changes and more.
Now I'm going to go over our novel idea, which is expanding the IR approach to include co-failure. First, let's take a look at the IR approach and two of its weaknesses. The first is the reliance on direct links due to names. That's where we use the consistent naming conventions in order to find the location of changes in the system and test cases that are related to those changes. Just as a reminder, this is what I'm talking about, where here we made a change in alter balance, and then we found all the test cases that involve that function. The other weakness is being unable to sort non-priority items, which I'm not entirely sure how to word, but what I mean is if you have all of these test cases here, you perform your scan to see which one to prioritize. So in this case, we take these top three ones, B, D, and G, and then we have all of these other test cases that are just under them with no real order to them. However, the odds of them all being equally likely to fail is extremely unlikely. So what can we do to sort these in a way that could be better? I believe the solution to that is to utilize the co-failure method that we found before. As a reminder, this was our co-failure discussion. It was used in CoDynaQ for test reprioritization. That was where if one test fails, what are the odds that another test fail? And then you keep a log of all those tests and derive some connections. So for example here, when we had test B fail, we immediately swapped test D to come next since it was extremely likely to fail as well. One thing I forgot to discuss before, but since co-failure utilizes results and purely results, it can find some hidden links between test cases. Test cases where they may not use the same functions, but they altogether have the same failure rate or a matching co-failure rate. So you can find cases that may be seemingly unrelated until you see when they fail. This is what I consider finding hidden links. Going back to this example, it's very clear, since this one has alter balance and this one has alter balance, test A and C, that if there's an issue one, there would probably be an issue with another. But consider a test case D that created an account. That doesn't directly interact with the balance, but if there was this restriction here, there could be a possible issue. Those possible issues, those co-failures that are unexpected, those are the hidden links that I believe could assist IR with things that aren't immediately scanned. It would also, using the co-failure rate, would allow us to give some priority to these items that are just still sitting in default order but delayed. So if we look at this example, we start with the initial list, and then we scan it using the IR approach. We find that B, D, and G are priority. We push those to the top and then push the others down. Now right here in this block, this is where the IR approach would end, and you would run the test cases exactly like this. For our novel idea, we believe that after you use the IR approach, you can then use the concept of co-failure to organize these items all below it. So for all these ones below it, what if you found the co-failure rates for the items up top that were a priority? You could find all of these rates and then pick the highest ones. So for example, you find here that this one has a 42% chance to fail whenever G fails. You would take the highest number in each of these rows for each test and then reorder it. So here we see 42 is the highest of all of the top percents, and that connects to F. So F would be the top of this previously unordered section. You keep filing it that way until you have a descending order of co-failure. Now, the top is sorted using the IR approach, and the next section is somewhat sorted using co-failure. It may not be perfect, but at least there is some priority where the items here in the middle are more likely to fail than the items at the bottom. We believe if you use this method in order to sort the sections at the bottom, the previously unprioritized, such as here, the unknown items, we believe this would assist greatly in helping these two weaknesses. Because we're using the co-failure rate, we can sometimes find hidden links, which would reduce the reliance on direct links, and then the non-priority items have some level of priority to them depending on the co-failure rates. So for this method, we believe just using this once would be sufficient to just at least have some priority for the entire list of tests, but you could also expand it so that you do the IR approach initially for just the first few tests, and then you could completely follow the reprioritization example, where after every failure, you check the co-failures and then swap around. We initially suggest the other method, being this one, because this way you can do all of the calculations for the test order before you even start. So you would have your changes, you would scan with IR, get your priority, and then you would look up the co-failure rates to sort the next section, and then this would be your final testing priority. You'd have to make no changes during the testing phase. If the overhead is not too expensive to swap testing, then maybe combining the two methods in its entirety would be effective as well. But we picked this one just so it's all front-loaded work and you just have to do everything once. Because ultimately, our goal was to fix these two issues. And we believe just doing it once, finding the co-failure rates once, is enough to help with these two weaknesses. And that is everything for our novel idea. We expand on this a little further in our paper, but this is the overview. Thank you.
In this presentation, we talked about the importance of regression test case prioritization and 8 different methods and ways in which to achieve it. We discussed a variety of approaches, which include the CoDynaQ single, a learn to rank, and the informational retrieval approach. We found the information retrieval approach by Raprier to be the most interesting, and that is why we wanted to use it as our novel contribution. We noticed the information retrieval approach is both simple and effective. However, there is a flaw within this method. There can be an issue in overlooking unprioritized tests. We discussed the possibility of including a co-failure method from CoDynaQ single, and it could be the answer to how the information retrieval approaches these methods. Co-failure would help ensure there are no methods overlooked that are maybe not necessarily directly related to the other test cases. We would love the opportunity to create and test this method. That is all for today. Thank you so much for listening.